Okay, hello everyone. This is a video to introduce you to work energy power and the common issues students have with work energy power. Right, we'll start with what is work done by a force on an object. Right, normally the force here is an external force. Right, and normally this is an object or system. Right, because work done is normally a way to represent the energy transfer into a system or out of a system. Right, so formally we define work done to be force times displacement. Right, note that S in this case is displacement times cosine theta, where theta is the angle between the force and the displacement as shown in this diagram over here. Right, so if this body is moving right, right, the force is in this direction over here. Theta is the angle between the force and the displacement. Right, if the angle between force and displacement is 0 as per this diagram over here, the work done is clearly positive and is equal to the magnitude of the force multiplied by the magnitude of the displacement only, because cosine 0, which is the angle between F and S, right, is 1, as can be seen from this diagram over here. Right, we can carry on seeing that as long as the angle between F and S is from 0 to 90 degrees, right, it is such that the work done on the system is always positive, right? So in this region here, work done is positive, or it means that work done by the external force adds energy to the system, right? Or the system will increase in energy. A simple example can be given in the form of a body moving right in this case, right? If this ball is moving right, the force is in this direction. This force will serve to accelerate the ball, right? And because it accelerates the ball, the kinetic energy of the ball gets higher and higher. Where does the added kinetic energy come from? Right, this force doing work done on the system, right? So the work done on the system is the energy added to the system, and this energy added to the system manifests itself as a increase in kinetic energy of the system, right? So we move on to case 2, which is the case whereby F and S are 90 degrees to each other. Right, when F and S are 90 degrees to each other, you can see that cosine theta is 0. Right, so cos theta is 0 means that work done is 0. Right, so anything 90 degrees to the motion, right, will actually, any force 90 degrees to the motion will not actually do work on the system, which means it cannot change the energy of the system, right? And part 3 of obviously, or actually even before part 3 I can show another example like that, right? If the displacement is in this direction and the force is like that, right? As long as theta is greater than 90 degrees, right, and underneath 180 degrees, right, the force will actually do negative work done on the system. How do we know? We can look at again this graph, right? You can see 0 is the threshold that we discussed just now, which case 2. After 0, cosine theta becomes negative, which means that the whole term of work done becomes negative, right? So once cosine theta becomes negative, this whole thing becomes negative, which means the work done by the external force on the object is negative, which essentially means that the force takes energy out of the system, right? So work done is negative means that the energy system the system's energy drops. Okay, so hopefully that clears up the initial part. I'll now move on to some misconceptions about change in energy. Alright, we'll look at the general formula for change in energy as final minus initial. Right, this is the same for all physics, regardless of whether it's scalar or vector. Right, in the past you should have studied that change in velocity is final velocity minus initial velocity, right? And now you study that change in energy is final energy minus initial energy. Alright, I'll give you two examples before I discuss the complicated part, which is this part over here. Right, in example 1 here, we have initial energy is 2 joules and final energy is 8 joules. Right, so if we want to find change in energy following this formula over here, right, it's final energy minus initial energy, which is 6 joules. Right, some people will put a plus in front to represent that this is a gain in energy, right? Because from 2 to 8, you basically gain 6 joules of energy. Right, so you can represent this as gain in energy is 6 joules, or you can say this as loss in energy is minus 6 joules. Right, so the loss will get rid of the negative sign over here. Okay, so this term over here in this square bracket is rarely used. You can ignore it if you are confused by it. Alright, we look at case 2. Initial energy is 8 joules, final energy is 2 joules. Alright, if this is the case, then final minus initial will be 8 minus 2, which you will get negative 6 joules. Now, Negative in a scalar and negative in a vector has very different meanings. Negative in a vector means that it's opposite to conventional positive. Alright? The negative in a vector has to do with the direction of the vector. The negative in a scalar has to do with the magnitude. Alright, so what this means is that minus 6 joules here means that the final value is 6 less than the initial value. Right, that's what the minus here means. Right, so the minus here means that the final value is 6 less than the initial value. Right, so the minus here has a meaning associated with magnitude because energy is a scalar. Right, so normally if I say that, for example, something has negative 6 joules of energy, right, without talking about change, what does it mean? It means that it has 6 joules less than 0. Alright, and that is a possibility when we discuss scalars. Right, scalars can be negative. Right, so an analogy that I like to give normally is money. Right, so if someone has $10 and someone owes you $10, right, the first person has positive $10. The second person has negative $10. The negative in the second person, right, has to do with his net worth being 10 less than 0. Right? The negative has nothing to do with direction because money is not a vector, money is a scalar. Right? So anyway, back to this, right? Change in energy is negative 6 joules in this context, case 2, right? Means that the gain in energy, I'll copy this one, is still minus 6 joules, but the loss in energy is 6 joules, which means that the negative here is actually gotten rid of when you discuss loss. Right? Because I already know negative 6 joules means that the final is 6 less than the initial. So when I talk about loss, I don't have to discuss the negative anymore because the negative means loss, right? Means less than already, right? So loss in energy is actually 6 joules in this context case. Right, so with this we can derive the formula for gain in energy and loss of energy. Right, so the general formula for gain in energy, as you can see from case 1 and case 2, should always be final minus initial, right? Because final minus initial is 6. 2 minus 8 is minus 6, right? So it's E final minus E initial. But this opposite from loss, because loss, right, you see, it's minus 6 here, right? How do I get minus 6? I actually need to take 2 minus 8. How do I get 6 here? I actually need to take 8 minus 2. So the formula for loss is actually initial minus final. Right? So when you're using these two terms, just be careful. Alright, gain the formula is exactly the same as change. Loss is opposite, right? For the reasons explained in this case, right? What does the negative 6 mean? The negative 6 joules in a change means that the final is 6 less than the initial, right? So I already know it's a loss, right? So if I take out the negative, then the loss is 6 joules, right? Basically the negative implies a loss, right? Right, so finally we come to the general equations, right? For conservation energy, we generally use the equation initial energy plus work done on the system, right? Again, work done here is defined to be by external force on the system, right? This can be positive or negative based on the theta in front we discussed, whether or not is 0 to 90 or 90 to 180, right? And this equals to final energy. Normally, initial energy and final energy will be inclusive of whatever mechanical energy is involved in the question, right? Normally it's initial, normally it's KE, GPE, and possibly elastic potential energy and some other form of energies as well, alright? And the second type of equation that we use is the loss equal gain type of equation, right? So loss in energy plus work done on the system, right, is equal to gain in energy of the so loss in energy of uh, a particular system must be loss in energy of a particular type of energy must plus work done must be equal to gain in energy of some other energy. Right. So normally this is used more in thermal questions. Right. So but I can give you an example over here. Right. So example of a ball dropping. Right. The loss in GPE is equal to the gain in KE. Normally you use this very roughly. Right. So but if you want to do it properly, right, it's initial GPE minus final GPE. And initial GPE is MGH, where H is the height above ground, right? And final GPE is MG0, right? So that's how the loss become positive, right? Because I take initial, which is this one, minus final, right? And gain in KE will be final minus initial, right? For the formula for loss and gain, please refer to this part over here. Right, so that completes the summary of the chapter that that this is a short summary of the common issues with the chapter on WEP.